Okay, so let's go back to geometry for a few minutes. Remember, we learned in geometry that if ever you are dealing with a right triangle and looking at any angle in that right triangle, and I could have chosen this one or even the 90-degree angle, doesn't matter, but any angle inside of a right triangle can be evaluated based on its relationship with all the other parts of the triangle. So I can look straight across the triangle from the perspective of the angle that I'm looking at here, and I could notice that that's the opposite. Or, of course, the hypotenuse is always the hypotenuse. I could look at the angle or the side that's right next to me, and I'd call that the adjacent because it's adjacent to where I live. I'm this angle, adjacent to me is the adjacent side, opposite is the opposite side, and then the hypotenuse is always the hypotenuse. So since I have three different sides to evaluate or to use, I can set up 6 different relationships or ratios. So I can look at the opposite side or take the ratio of the opposite to the hypotenuse, or I could look at the adjacent to the hypotenuse, or I could look at the opposite over the adjacent. And in fact, each of these are the primary trig functions. So the first one, the opposite over the hypotenuse, that's sine theta. So the sine, we give a name to the function. The sine of this angle is whatever the ratio is of the opposite over the hypotenuse. The adjacent over the hypotenuse is the cosine of that angle, and the opposite over the adjacent is the tangent. And I'm using the shorthand because I know you've seen this before, and so I don't feel that I need to write out the longhand words for you. So there's another way to look at each of these. I could make a ratio of the opposite over the hypotenuse, but I could also have chosen to write a ratio using the hypotenuse over the opposite. And in that case, I would get a different ratio than the sine of theta. The hypotenuse over the adjacent would give me a different ratio. And the adjacent over the opposite, would give me a different ratio. In fact, notice that this is the inverse of the sine theta. This is the inverse of cosine theta, and this is the inverse of tan theta. And so we could actually call this just the inverse of sine theta and the inverse of cos theta and the inverse of tan theta. But rather than dealing with that, we gave them all their own name. I say we like I had a role in it. I didn't, by the way. I'm not that old. The inverse, the name for the inverse of sine theta is cosecant theta. Shorthand is CSC for cosecant. The inverse for cos theta is secant, theta. And the inverse for tan is cotan theta. Now, it would be really nice if the mathematicians that developed this math would have taken a minute to recognize that it would have been so much easier to call the secant the inverse of sine because they both begin with an S, and the cosecant the inverse of cosine because they both begin with a C, but they weren't thinking in those terms. They didn't do it. We just have to learn to adjust. And of course, it goes without saying, but I'm going to say it anyway, that cosecant can be written as, the inverse of sine could be 1 over cosecant. The inverse of cosine could be written 1 over secant, and the inverse of tan could be written as 1 over cotangent. So they're inverse relationships between each other, the 3 primaries and then the inverse relationship. So let's set up a triangle and do an example. I'm going to write the right triangle, ABC, and I want to evaluate theta. So the hypotenuse length is 65, the length of BC is 33, and the length of AB is 56. And so let's write the 6 trig ratios for this triangle. I'm going to move it over just a little bit. I got that awfully close. Okay, so the trig ratios. Sine of theta, this is theta. I want the opposite over the hypotenuse. And these don't reduce. If they reduced, I would want to, but they don't reduce, so I'm going to keep it that way. The cosine of theta is the adjacent over the hypotenuse. Again, that's as reduced as it goes. And then the tangent of theta. Now this would be a good place to add. The tangent of theta is actually the same thing as the sine of theta over the cosine of theta. So if I were to use that version, well, let me use this version and then I'll come back to the actual triangle. Well, if I write 33 over 65 for sine theta, and then 56 over 65 for cosine theta, the denominators multiply by the reciprocal of the denominator, so the two denominators would disappear, and so I'm left with 33 over 56 is the tangent of theta. And if I look here, I'm looking for tangent to be opposite over adjacent, so the opposite is 33 over the adjacent is 56. 33 over 56 is exactly what I got. And so the last three would be cosecant theta, whoops, not spelled that way. The cosecant theta is the inverse of sine theta, so that would just be 65 over 33. The secant theta is the inverse of cos, so I just flip those, 65 over 56. And then the cotan, I don't know where I want to write that. The cotan of theta would be the inverse of the tangent of theta, so that's just 56 over 33. So in this triangle, for theta, these are the 6 trig ratios. If I were to look instead of theta at beta, then I would get a different set of trig ratios. Notice though, since I only have these 3 numbers to work with, and the 6 ratios are exhaustive for the patterns, if I evaluate beta in the same triangle, I'm actually going to get inverse relationships between the different angles in the triangle as well. So that's a pretty exhaustive and thorough way to explain a triangle. And we are going to use that extensively in our next unit. So let's do another example, kind of evaluate from a slightly different perspective. I'm going to sketch out a triangle, even though it's not given to us in the beginning. We're told that the sine of theta equals 1/3 for the triangle you're looking at. And our task is to find all the other trig ratios. Well, let's start with, we know that sine theta is opposite over hypotenuse. Since that's true, I know that the length of the hypotenuse has to be 3. And the length of the opposite side from the angle I'm talking about, theta, has to be 1. Since I haven't been given a diagram or any instructions about where theta is, I can choose. So I'm going to call this theta. It can't be this one, the right angle, because the right angle would be opposite over opposite, which doesn't really work. And so it has to be one of the other angles. So I'm going to call, if this is theta, then I'm going to call this side length 1. And now all I need to do is find the length of the third side. I have a way to do that, thank goodness. I know that c squared equals a squared plus b squared. So I have c, and let's say I have a. Let's solve for b. b equals the square root of c squared minus a squared. So in this particular case then, we're looking at the square root. C squared is always the hypotenuse, so that's 9, minus 1, which equals the square root of 8. There's a perfect square 4 contained in 8, so 2 root 2 is the length of the third side. Now I can finish up my work. Cosine theta is the adjacent to root 2 over 3. Tangent theta is the opposite over adjacent, 1 over 2 root 3. 2 root 2. But we don't really like to have a radical in the denominator, so I'm going to multiply both the numerator and the denominator by root 2, which gives me a root 2 over 4. And now all I need is reciprocals. So the cosecant of theta is 3 over 1. The secant of theta is 3 over 2 root 2. Again, rationalizing the denominator, 3 root 2 over 4. And then the cotan of theta, I'm not going to worry about this one because I would just put a radical back in the denominator. I'm going to go take the reciprocal of what I had for tan, originally had for tan, and I get 2 root 2. So these are all answers in the exact value. I can use a calculator to find approximate values if I want to. I'm going to find them just for the inverse ratios or relationships. Well, 3 divided by 1 would just be 3, so the approximate value for cosecant is the exact value. But for secant, if I start by finding root 2, and I want the approximate value for root 2, so now I have a value. If I multiply that by 3 and divide by 4, 1.0607. Let's see if I've made a mistake. My approximate value times 3/4. Nope, I'm good to go. And then for cotan, I'll go back up here and get my approximate value and multiply that by 2. And so my approximate value, I should put squiggles for approximate, for the cotan of this angle is 2.8, and I'm going to say 2.828. I guess there's no time like the present if you later go on to take the AP exam for calculus. 3 decimal places is standard, so in the first case I would have 1.061. Although for trigonometry, I don't really care how many decimal places as long as it's meaningful. All right, so let's do another type of problem, another example. If I'm given a triangle, it's a right triangle, and I have one side length as a variable. I don't know the other side length. I know the hypotenuse is 7, and I know that I have an angle that's 35 degrees. We can use trigonometry to find the value of x. So what would this side length be? If I have the length of x and I have the hypotenuse, or if I have any 2 side lengths, I can use the Pythagorean theorem to find the third if I want it. So let's use trigonometry to solve for x. Well, I'm looking at 35 degrees and I'm looking at a hypotenuse. So I can make a ratio with the hypotenuse in the denominator would be 7. And x in relation to the hypotenuse is not opposite, it's adjacent. So x is the adjacent. So which ratio is the adjacent over hypotenuse? That's the cosine of theta. So that would be the cosine, and theta, my angle is 35 degrees. So now I can solve for x just like in a regular algebra problem. I have x. I'm going to multiply both sides by 7, so I get 7 times the cos of 35 degrees. And so x equals, well, I need to know what this is. I don't have any values for the cosine of 35 degrees that I can just substitute for that. So I'm going to go to my calculator, and the instructions have actually asked that I round to the nearest tenth. So let's use, first I want to make sure I'm in degrees because these are both degree measure, and my calculator is definitely in degrees. So I'm going to put in cosine, which is this yellow button. It's this button, but yellow. Cosine is written in yellow above, so I'm going to use the yellow button to get to it. and then press cosine. It lets me put in cosine. 35, and I have to close the parens on my calculator. And now I want it to be an approximate value, so I can press the diamond and enter, and it'll give me a decimal. If I don't press diamond enter, I'm actually going to get a decimal in this case no matter what. Oh, well, actually that's not true. I ask without pressing the diamond because I'm set for exact values. My calculator, there is no exact value. There's no pretty value like this that gives me just straight pretty numbers to work with. There's no exact value, so in that respect, cosine of 35 would be considered prime-ish. And so the calculator just gives me back the same thing I put in. But that's okay, because I'm up here where I have an approximate value. I'm going to go back up and get it. And now I'm going to multiply that by 7. So 5.7341. We've been asked to round to the nearest tenth. So 5.8. No, it's not a roundup. 5.7. And this is an approximate value, so I should indicate that. Okie dokie, artichoke. That is a quick review of your basic trig functions learned first in geometry and reviewed today.